The James Webb Telescope found something that's keeping scientists awake at night. A galaxy so old and so big that it simply shouldn't exist according to everything we know about the universe. It appeared when the cosmos was only 300 million years old. That's like finding a fully built skyscraper in a city that just started being constructed. This galaxy is bigger and more developed than anything we thought possible at that time. Scientists are having to rethink everything about how the first stars and galaxies formed, and the most disturbing thing of all, if this galaxy shouldn't exist but does, what else about the early universe do we have completely wrong? What will this discovery reveal about the first moments after the Big Bang? Subscribe to the channel, leave your like, and comment from what part of the world you're watching. Get comfortable and relax. Let's begin. How is it possible that a galaxy so big and mature already existed when the universe was still a toddler? That's the question astronomers grappled with after the James Webb Space Telescope spotted a distant, brilliant galaxy whose properties don't seem to fit our accepted understanding of the cosmos. To appreciate how groundbreaking this discovery is, imagine what astronomers have spent decades trying to understand about the first few 100 million years after the Big Bang, which is believed to have marked the beginning of our universe about 13.8 billion years ago. Before the James Webb Space Telescope, or JWST, it was never possible to see clearly that far back in time. The further we look in space, the further back we see in time, because light from those ancient objects needed to travel across the universe for billions of years to reach us. The JWST, with its sensitive infrared instruments, has given humanity eyes sharper and more sensitive than any telescope before, allowing us to observe stages of the universe that were previously completely invisible. A major moment in this quest occurred when the JWST data revealed a stunningly mature galaxy only a few 100 million years after the Big Bang. For context, astronomers refer to these earliest epochs as the cosmic dawn, a period characterized by chaos, density, and energetic birth of the first stars and galaxies. Before this recent discovery, cosmic models predicted that early galaxies forming at this time should be small, irregular blobs made up of a few scattered stars. Nothing like the majestic spirals or bright ellipticals that fill the modern universe. Instead, JWST showed something no one expected, a galaxy that seemed already massive and complex, complete with distinctive and well-developed features. It wasn't simply a detection of dim light or a fuzzy dot. This object was unexpectedly bright, indicating not just a high mass, but a level of organization and star formation that current models said should be impossible so soon after the universe began. So how did the scientists actually find this galaxy? They were searching a patch of sky, looking deeper than ever before in the infrared, which allowed them to see objects whose light started its journey toward Earth over 13 billion years ago. Through its primary mirror and detector, JWST can capture faint red-shifted light, which means it picks up wavelengths stretched out by the universe's constant expansion. Generally, galaxies that are distant enough to appear as they were, at just a few 100 million years after the Big Bang, should be extremely faint, barely detectable, as blobs of light, even with JWST's extraordinary precision. Yet this particular galaxy blazed forth with brightness and definition. It was as if a photograph from a family album of cave-dwelling ancestors revealed someone in a suit walking down a city street. The images showed clear signals that the galaxy contained significant mass in stars already assembled, and the light curve matched expectations not of an infant galaxy but of something far more mature. What really made jaws drop were the features the JWST picked out from this ancient galaxy. There were structural markers indicating a developed form. The starlight was not primarily bluish, the tint usually associated with ongoing rapid star formation from chaotic clouds of gas, but rather suggested a population of older stars mixed in. The core appeared to have a level of brightness and density comparable with much older, nearby galaxies. It may have even exhibited hints of rotational structure, the kind of organization seen in established galaxies. That means either stars started forming at a breakneck pace right after the universe cooled enough for atoms to exist, or the processes that astronomers believed governed early cosmic evolution might not be complete. The technical capabilities of JWST are the only reason we can see and study this galaxy in such detail. The telescope's massive gold-plated mirror spans 6.5 meters in diameter, collecting and focusing far more light than any previous observatory. The key is JWST's ability to see in the infrared spectrum, which is essential because light from ancient objects is stretched or redshifted by the expansion of space over billions of years. Older telescopes like Hubble operated largely in optical and near-infrared wavelengths, but could not spot the most distant, oldest galaxies. With JWST's sensors built to operate in a cold, dark environment far from Earth, astronomers were finally able to peer across not just enormous distances, but enormous stretches of time, opening a new window onto the universe's first hundreds of millions of years. For scientists in the field, this observation is akin to discovering a fossil that predates what you thought possible for the evolution of life. It doesn't just revise a date in a textbook, it forces a rethink of the entire timeline and process. Prior cosmological models predicted that galaxies in this early period of the universe's existence should have remained small, clumpy, and relatively dim, consisting largely of hydrogen and helium sprinkled with the first stars. These stars should have taken tens or even hundreds of millions of years to group together under gravity into anything resembling a large galaxy. But what JWST found was a galaxy already an order of magnitude more mature, throwing a wrench into calculations about the rate at which matter can organize itself under the laws of physics as we understand them. Part of the reason this single finding is so impactful comes from the way cosmologists build their models. They do it like engineers assembling a bridge, making sure every step follows logically, using measurements, simulations, and a lot of cross-checking to ensure everything connects. Observational astronomy has long operated under assumptions grounded in the lambda cold dark matter model, considered the backbone of our understanding of cosmology. This model explains how matter, primarily dark matter, coalesced over time, setting the stage for the slow assembly of the earliest galaxies and stars over hundreds of millions or billions of years. The discovery by JWST throws this careful sequence into doubt. If a massive and mature galaxy is seen forming a mere 300 million years after the Big Bang, it suggests either the model is incomplete, missing some crucial physics, or something entirely new is going on. In practical terms, astronomers started double and triple checking their data. Maybe the galaxy was just closer than it looked, and its red color was a trick of cosmic dust or some other effect. But further analysis confirmed the extreme distance and the age of the light. The data left little room for error. This was indeed a giant, well-built galaxy at a staggeringly early time in the universe. The discussion quickly shifted from questions of measurement or technical error to questions about physics itself. The timeline of galaxy formation, based on millions of observations and years of careful simulation, suddenly had a gaping hole right where this galaxy lived. This matters because, in astronomy, seeing something unexpected almost always triggers new hypotheses, and sometimes revolutions in our understanding of nature. The main questions spawning from this discovery include: how could so many stars have formed so quickly? What fueled the rapid assembly of enough matter in such a short time? Did the dark matter in the universe behave differently in its earliest epochs? Was star formation somehow more efficient under early universe conditions because of higher densities or unknown mechanisms? Each question leads to new investigations, tighter models, and a race among research teams to see what else JWST might reveal lurking in the cosmos. Behind all these scientific questions is the fact that the universe appears more dynamic and surprising than previously thought. The capability of JWST to spot such galaxies with incredible fidelity marks only the beginning of a new era of discoveries. Scientists are now combing through terabytes of data, searching for more examples, and building more complex simulations to understand how such a galaxy could have come together so fast. As they do this, there's a building sense of excitement, not hype, because astronomy is a field driven as much by skepticism and curiosity as by confidence in what's currently known. In one stroke, This find pushes everyone to rethink their assumptions about the cosmic dawn. It's important to recognize that this one observation does not entirely rewrite the story of the universe, at least not yet. But it does force astronomers to go back and check every step, like tracking down why a recipe that always made 10 cookies unexpectedly yielded a cake. Some will argue that this galaxy is just the rare, brilliant outlier, a product of random chance or gravitational lensing, making it appear brighter and more developed than it is. Others argue that the model is missing a fundamental ingredient, like new physics regarding dark matter, exotic forms of energy, or an unexpected pattern in how gas cooled and formed stars. However it's explained, the observation itself is a data point that cannot be ignored. One technical point that illustrates just how exceptional the JWST's contribution is lies in its ability to distinguish the underlying physical processes at play. Astronomers analyze the light coming from the galaxy, breaking it down into individual colors or wavelengths, a process known as spectroscopy. With this information, they can estimate not just the galaxy's age, but how many stars it contains, what kinds of elements are present, and even whether there are signs of black hole activity or intense bursts of star formation. The JWST's sensors have made it possible to pull out such details at distances where, before, astronomers were working with nearly featureless specks. It's as if the difference between seeing a single candle and the full skyline of a city was suddenly abolished. The galaxy's light contains another important clue. By analyzing its spectrum, researchers can infer how long some of the stars have existed. Instead of seeing only hot, massive, young stars, which would indicate a totally fresh galaxy, they found signatures of older stars, meaning that significant star formation must have started not long after the Big Bang itself. This shortens the presumed time it takes to build up a galaxy by hundreds of millions of years, putting pressure on all the current ideas about star and galaxy formation. If stars actually began forming at a much earlier stage and could organize themselves into large structures faster than anyone guessed, the entire scale of cosmic history shrinks. At this point, it's also worth touching on what astronomers do when they get data this surprising. They begin by consulting other measurements and theories, like simulations run on supercomputers of how the first galaxies might have formed under different cosmic conditions. They check if the newly observed galaxy could have merged from smaller galaxies faster than thought possible, or if maybe the intense brightness is due to a supermassive black hole, an active galactic nucleus, or some other exotic process. Yet even these scenarios struggle to fit the brightness, mass, and apparent structural sophistication revealed in the JWST image. No easy explanation yet bridges the gap between prediction and reality. That's part of what makes science exciting. An anomaly like this pushes the entire community to chase new explanations, gather more evidence, and sometimes make conceptual leaps. In summary, the detection by the James Webb Space Telescope of a mature, massive galaxy, when the universe was only around 300 million years old, has thrown a challenge at astronomers. It was only possible because of JWST's exceptional sensitivity to infrared light and its ability to observe the earliest epochs of the universe with unprecedented clarity. Far from being a mere curiosity, this observation opens up new questions about the speed and mechanisms of galaxy assembly, the behavior of matter in the early universe, and even whether our most enduring models still hold. What we learn from this one galaxy might, in time, reshape our understanding of everything that followed. Did you ever wonder why finding a giant galaxy soon after the Big Bang has left astronomers so puzzled? To understand this, you have to look at what scientists have believed about the early universe for decades, and how timelines shape their expectations. When researchers talk about the beginning of everything, the numbers can seem almost too big to grasp. The Big Bang, which is thought to mark the origin of our universe, happened about 13,800 million years ago. Right after that, everything was hot, dense, and packed full of energetic matter and light. Conditions were so extreme that atoms as we know them could not even form for hundreds of thousands of years, let alone something as complex as a star or a galaxy. As the universe kept expanding and cooling, it reached a point a few 100,000 years after the Big Bang when atoms, mostly hydrogen and a bit of helium, finally came together, and the universe became transparent. That means light could travel freely, but even then, there was nothing like stars or galaxies yet. The universe was basically a dark, invisible sea of simple gas. For millions of years after that, astronomers think gravity began pulling together small clumps of this gas, but it would have been an extremely gradual process, starting from tiny, random differences in density spread through space. Now, according to the most widely accepted theory among astronomers, something called the lambda cold dark matter model, it is expected that the first stars began to ignite maybe 100 million to 200 million years after the Big Bang. These very first stars, sometimes called population 3 stars, would have formed inside the densest patches of gas, and they would have been huge, hot, and short-lived. Once these stars exploded as supernovas, they would seed their surroundings with slightly heavier elements, carbon, oxygen, and so on, making the next round of stars slightly different. What comes next is important. According to theory, the first real galaxy's collections of stars bound together by gravity should not appear in any organized way until several 100 million years after the Big Bang. Early versions would look like lumpy clouds, irregular and chaotic, assembled in a slow, step-by-step fashion. Bigger, well-formed galaxies would require even more time, often between 1 billion and 2 billion years after the Big Bang. The reason for such a slow process, according to models, is that matter in the early universe was distributed lightly across vast distances, and only over long periods could it fall together into the kind of dense structures we can spot today. When you think about that timeline, it seems clear that astronomers did not expect to see fully formed massive galaxies in the earliest slices of cosmic history. Everything from how gas cools and comes together to how efficiently stars can form from that gas was thought to set natural limits on just how quickly big galaxies could possibly come to life. The lambda cold dark matter model in particular was seen as robust because it matched many observations of the universe as we see it today. It explained the way cosmic structures are arranged over great distances. It described how galaxies grew by swallowing smaller neighbors, and it even made sense of subtle patterns in the cosmic microwave background, the faint leftover light from the Big Bang itself. What throws a wrench in all of this is the discovery, using the James Webb Space Telescope, of a galaxy that looks not only giant but also impressively mature, shining bright only 300 million years after the Big Bang. That's incredibly early, so early that under standard assumptions, a galaxy of this kind shouldn't exist because the universe was supposed to be too young and chaotic for anything so well formed to have come together. Instead of catching a glimpse of a tiny, unorganized blob, astronomers saw signs of substantial mass and structure, which simply do not line up with the timelines everyone had in mind. The reason scientists are so taken aback is not just the existence of this single galaxy, but what it says about the whole process of cosmic evolution. There is a set of rules in place about how fast matter can gather, how quickly stars can form, how efficiently large reservoirs of gas can cool and condense, and how cosmic expansion affects everything. Current theories, based on a mountain of observations and simulations, say all these processes add up to a universe that needed a lot more time, with galaxies taking at least 500 million years, if not much longer, to amount to anything more than faint, scattered collections of new stars. Picture what has to happen for a galaxy to look like the one found by the James Webb Space Telescope. You would first need large amounts of gas to collapse under gravity, a process that is naturally slow because radiation from the first stars heats up surrounding gas and makes it harder for more stars to form. Then, you would need those clouds of gas and stars to merge together, over and over, through cosmic collisions, a process known as hierarchical assembly. On top of that, all the while, most models assume an invisible component called cold dark matter is guiding and anchoring these structures. The mass, brightness, and apparent complexity of this early galaxy suggest that the universe found a way to fast-track these steps, or that the models themselves need major tweaks. When theoreticians tried to model galaxies in the universe's first 500 million years, the results almost always showed small, faint, and misshapen objects. These early galaxies should barely be stable and still be in the process of forming. What astronomers now see is exactly the opposite, a galaxy that looks like it skipped the expected stages. This is where a key concept comes in. Cosmic timelines are not just guesses, they are the sum of physical limits, feedback loops, and measured quantities from the early universe. For example, there are strict limits on how fast stars can form, because radiation and winds from the first stars blow gas away, shutting down new star birth in the process known as stellar feedback. There are well-known cooling rates for hydrogen gas, which set a minimum time for a giant cloud to cool off enough to collapse into stars. All of these rates feed into computer simulations, which then produce the population of galaxies we are supposed to find at each stage. When you see something way out of place in that timeline, like a mature galaxy just 300 million years after the Big Bang, it calls the entire set of rules into question. Is something missing in the understanding of how gas cooled in the early universe? Could dark matter be more efficient in pulling things together than previously thought? Is star formation in dense patches happening at a rate higher than the current estimates? These questions are more than mathematical puzzles. They strike at the heart of how astronomers build a history of the universe. So why does the lambda cold dark matter model say this kind of galaxy should not exist? It sets up several bottlenecks at each stage in galaxy formation. Early on, after the Big Bang, free electrons and radiation kept matter from clumping together. Once things cooled and atoms formed, matter still needed to overcome expansion and resist being blown apart by the first supernova explosions. Overcoming these hurdles takes time, especially on the scale of hundreds of millions of years. By the timeline, big, organized, star-rich galaxies simply should not turn up until much later. Now that the James Webb Space Telescope has shown evidence of the opposite happening, there is a scramble to see what might fill the gaps. The telescope's incredibly sharp, infrared vision allows us to look much deeper into the universe's past than before. When astronomers analyze the images, they look for clues about the age and mass of galaxies by measuring how stretched the light is, something called redshift, which tells you how long the light has been traveling. The further away a galaxy is, the higher its redshift value. This discovery has one of the highest recorded redshifts for any bright, structured galaxy, pushing right up against the edge of what theory allowed. Scientists have started to wonder if certain physical processes are working differently than expected in this early era. Is it possible that the very first rounds of star formation produced massive stars with such intensity that new generations of stars formed even more rapidly out of the leftovers? Could the gas clouds be cooling down much faster in areas where dark matter was especially dense? Did giant black holes jumpstart the formation of galaxies by collecting enormous amounts of gas and making starbirth more efficient around them? The answers are not simple or immediately obvious, but all these possibilities are now actively being investigated with new models and simulations. Another element of the puzzle involves the material needed to build a massive galaxy. There needs to be a process for making lots of stars out of available gas in a short window of time. If you imagine the universe like a cosmic kitchen, the recipe for making a galaxy includes mixing enough ingredients, heating or cooling things in the right sequence, and giving the whole mixture time to blend together. The timeline is set by how efficiently the universe cooks. If it is slower than expected, you get fewer, smaller galaxies. If it is faster, you get outliers like this one spotted by the James Webb Space Telescope. Astronomers are trying to figure out what changed in that cosmic kitchen. Maybe the ingredients were not distributed as evenly as once thought. Maybe certain regions had far more dark matter or denser clouds of gas, which made it easier for a galaxy to get big fast. Or maybe there was some completely new process that pushed things along, something yet to be identified in observations or calculations. A further angle scientists are exploring has to do with the population of galaxies at this early stage. Was the discovery just a one-off? Or are there many other hidden galaxies that are big, bright, and well-developed, lurking in JWST images? If more of these are found, it would mean a systematic error in our understanding of the entire early universe. On the other hand, if galaxies like this one are extremely rare, Maybe a special combination of conditions allowed just a few fast-track galaxies to form much earlier than anticipated. So why do these questions matter? Astronomy is all about connecting the dots between observations and theory. The lambda cold dark matter model has had tremendous success in matching what we see in the later universe. The way galaxies are clustered, how they move, and the structure of galaxy clusters across huge stretches of space. But every model is based on thousands of assumptions and parameters, all built up from evidence collected from telescopes, satellites, and particle experiments on Earth. If the model cannot explain what is seen at the edge of the observable universe, then the roadmap for cosmic evolution may have a major detour that everyone missed. This could mean that, for certain time periods, things like gas cooling rates, star formation efficiency, or gravitational effects from dark matter are different than what is measured in more recent times. The tension between theory and observation often leads to new scientific breakthroughs. Each new surprising result pushes researchers to revisit old ideas, develop new ones, and improve the tools for collecting and interpreting data. People working in the field now have new motivation to build bigger computer simulations, check the fine print in their models, and ask whether the rules set for the early universe really hold in light of discoveries like this. Astronomers are also looking deeper into the possible roles of feedback, how new stars and supernovae blow bubbles in the surrounding gas, regulating the speed at which galaxies form and grow. Earlier theories said this feedback process slows things down, but if something about the first stars made feedback less effective, then early galaxies could grow at a much faster pace. It could also be the case that dark matter, still mysterious and never detected, directly operates differently when the universe was much younger and denser. There is a lot of interest in checking if the numbers are right. Researchers have to be certain that the galaxy's distance, mass, and brightness are not being misread. They double-check the calibration of instruments, compare with different methods of measuring redshifts, and look for sources of error or confusion. For example, sometimes a bright foreground object could distort the view, or an unusual alignment could make a distant galaxy look bigger than it actually is, a phenomenon called gravitational lensing. However, at present, the evidence is strong enough that astronomers feel confident the galaxy is not an illusion, but a real early heavyweight. With all these questions still open, the discovery is not a crisis for astronomy, but a chance for learning. The history of science shows over and over that when nature hands you something unexpected, you adjust your theories to account for reality, not the other way around. If more JWST data confirm that galaxies can indeed form and mature at such incredible speeds, people may need to introduce new ingredients to the recipe of cosmic evolution, perhaps ones that make the earliest epochs more varied and dynamic than previously supposed. In the end, the reason the galaxy shouldn't exist is that the timelines set by current cosmological models do not allow the universe enough time to build such a massive and mature object so soon after the Big Bang. It pushes everyone to rethink the speed limits of galaxy formation, the efficiency of the processes involved, and even the basic physical laws assumed to govern the early universe. Whether the explanation involves tweaking feedback effects, changing assumptions about dark matter, or something completely new, this discovery stands as a reminder that cosmic history is still being written. Astronomers will keep testing, refining, and rethinking, and each startling result like this adds a fresh page to what we know about how the universe moved from chaos to structure. Trying to grasp why this early, massive, mature galaxy is such a difficult fit for our understanding, it helps to step into the shoes of the scientists looking at the raw data. When they first saw the light from this galaxy and calculated how far back in time it was, the reaction was one of real surprise. Often, astronomers have a clear picture in their minds about what the early universe should look like. They are used to seeing scattered, clumpy galaxies, little patches of stars that are just starting to come together. Yet suddenly, with this new evidence, the standard idea took a hit, because this galaxy was not just bigger, but already showing features that signaled organization and structure usually thought to take much longer to develop. In the world of astronomy, when an object stands out as an exception, one of the first steps is to double-check the basics. Scientists check if the measurement is right. They want to make sure that nothing in the foreground is making a distant galaxy look brighter than it is, a phenomenon that can happen if a nearer object bends the background light with its gravity, essentially acting as a lens. In this case, the JWST team worked to rule out these possibilities. They used different methods to estimate the distance and brightness, comparing data from other telescopes and reanalyzing the spectral fingerprints. They confirmed that the light truly did come from a galaxy that formed only about 300 million years after the universe began just a tiny fraction of the universe's age. This confirmation left astronomers with a real puzzle. One of the striking things about the JWST discovery is how quickly a galaxy could grow large and form stars so efficiently in such a short time. It does not fit the gradual, steady path that standard theory predicted. Models suggested there should be a slow climb from the first small groups of stars to bigger, more mature systems over the first billion years or more. And yet, here was a galaxy that looked like it belonged much further along in cosmic history, already bustling with star formation, showing signs of mass and density that even some older galaxies today would envy. What makes this discovery dramatic from a research perspective is that it brings together many layers of galaxy science that usually only show up after vast stretches of time. Building a galaxy is not just about putting together stars. There is a process involving gas cooling, gravity, collisions, starbursts, and feedback where energy from young stars blows into the surrounding gas and can limit future star births. For a galaxy to reach a massive size and mature look, all those steps should have needed a lot more time, according to what astronomers thought. The gas in the early universe was very hot and sometimes ionized, making it harder for stars to form in compact groups. Cooling the gas enough to collapse and form stars efficiently should have been a slow bottleneck. And yet, this object appeared to have pushed through those limits faster than expected. Another part of the surprise comes from the structural features seen in the JWST data. Astronomers do not just look at a single point of light, they can analyze the distribution and the way light is spread across the galaxy to find signs of disks, bulges, and sometimes even spiral arms or dust lanes, especially when the telescope's resolution is as sharp as what JWST can offer. For an object this old in the universe, seeing any sign of a central concentration or structure is extraordinary. It suggests not just rapid star formation, but a gathering and settling process that science thought needed hundreds of millions more years. What a lot of people do not realize is that the detection of older stars in this kind of object only adds to the question. When astronomers check the galaxy's color, they see it's not just bright in blue, which would signal a wild nursery full of only brand new hot stars. Instead, some of the galaxy's light is more muted, with hints that older, redder stars contribute too. This means that the first burst of star creation must have happened even earlier, and on a huge scale, with stars living out their lifespans in a surprisingly quick timeline. For that to happen, the gas had to come together, cool, and spark ongoing rounds of star formation almost immediately, pushing earlier than anyone expected on the cosmic calendar. Up to now, most researchers believed that the earliest galaxies were unruly and fragmented due to violent processes in the young universe. Collisions and merging between little clumps would have been common, but the result should look chaotic, not organized. The evidence of a mature system so quickly means that maybe either these processes work differently than once believed, or something else was speeding things up. There could be factors like unusually dense regions of dark matter, which help gather material more quickly, or different cooling and feedback effects in the very first generations of stars. Teams using JWST are also able to dig deeper by looking at the chemical signatures in the galaxy's light. When massive stars die in explosions called supernovae, they spread heavier elements into space. If a galaxy contains these heavier elements like carbon, oxygen, or nitrogen, it shows that multiple generations of stars have already lived and died. Finding such signatures in a galaxy this early means the process of star birth and death happened not just once, but several times in a very short span. This goes against the long-held belief that the first galaxies would have little in the way of these elements, and instead be almost entirely made of hydrogen and helium left over from the Big Bang. Additionally, there is attention on how the light from this galaxy has traveled through space for over 13 billion years. The fact that JWST can capture and break down this faint, stretched light into meaningful data is a leap over what older telescopes were able to do. For example, Hubble could reach into parts of the early universe, but its equipment was optimized for visible light, and it missed many of the very oldest, most redshifted objects. The JWST's infrared instruments changed the game, giving access to this uncharted territory in cosmic history. It allows astronomers to see these impossible galaxies with clarity and collect detailed information about their size, age, brightness, and even how much dust and gas they are shedding. When the news of this discovery spread, you saw astrophysicists around the world brainstorming what could explain such a rapid jump to maturity so early on. Some are revisiting computer simulations, tweaking the initial conditions, and trying out different assumptions on the efficiency of star formation under various scenarios. There is consideration for how black holes might help drive the evolution of these early galaxies, perhaps by acting as gathering points that cause massive inflows of gas and trigger large-scale bursts of star creation. There is also an interest in whether the makeup of the early universe was different in certain regions, giving some galaxies a head start over others. Making sense of this situation, one avenue researchers are exploring is the rate of growth through galaxy mergers. The idea is that many smaller galaxies might collide and merge into one giant much faster than previously calculated. When galaxies smash together, their gas can compress, rapidly forming new stars and building up mass quickly. However, even with this mechanism considered, the overall timescale still seems tight against the limits that standard models set. If the process really happened that quickly, it could imply that dense zones or special pathways were more common in the young cosmos. There is also a renewed focus on feedback from the earliest stars. Some researchers propose that the first massive stars might not have thrown out as much energy as once thought, or that they did so in a way that was less effective at stopping further star formation. With weaker feedback, more gas would stay in place, leading to faster and more continuous star birth. Alternatively, early star-forming regions might have been shielded from harsh feedback by surrounding clouds, letting the galaxy grow without much interruption. The impact of this galaxy's existence ripples out to the ways in which models are set up. The cosmological simulations that have guided the field so far rely on rules about how gas cools, how stars ignite, and how feedback works over time. If those rules need updating, especially for the very earliest cosmic periods, that has implications for describing the history of structure in the universe, as well as the distribution and evolution of stars, galaxies, and possibly even black holes. Now, each of these ingredients is up for review as teams compare predictions from models to the new observations from JWST. Meanwhile, astronomers are also looking for support from future data. The hope is to find out if this mature galaxy is an isolated case, potentially made possible by a freak alignment of chance conditions, or if more examples are waiting to be found. The JWST mission is designed to stay operational for at least a decade and survey even wider patches of sky, letting astronomers cast a bigger net for similar galaxies. If the pattern repeats, that will make a strong case that the early universe was more efficient at making big, organized galaxies than anyone had thought. The confirmation of this early mature galaxy not only changes the questions, but deepens them. It forces astronomers to ask about what invisible processes could be at work, or if something fundamental is off in the ways they interpret the oldest light. The scientific community is now far more open to considering new mechanisms that speed up the formation of stars and galaxies in the universe's first few 100 million years. With JWST acting as a kind of time machine, every surprising result now pushes people to expand their ideas, run more experiments, and make room for what the universe is actually showing rather than just what the models predicted. The story keeps unfolding with each new detection, each cross-check on the data, and each round of thinking about what it takes for a galaxy to get big and mature in such a short span after the universe's earliest light. It is a genuine shake-up, but also the kind of challenge that makes astronomy such an active and fascinating field, always keeping scientists on their toes. As more data comes in, and as simulations get better, this unexpected galaxy remains a prime example of how much this young universe still has to teach about the forces and processes that shaped everything people see in the cosmos today. As astronomers continue to dig into what this early, surprisingly massive galaxy means for our picture of the universe, the conversation quickly circles back to the standard model of cosmology, which is basically the blueprint that has guided years of theories and calculations. This standard model, most commonly known as the lambda-cold dark matter model, often shortened to the lambda CDM model, has served as the framework for understanding almost everything about how cosmic structures form and evolve. It gives scientists a way to link the initial conditions of the universe, right after the Big Bang, all the way up to the present-day distribution of galaxies, clusters, and even the tiny variations in the background radiation left over from the Big Bang itself. To really grasp what's at stake, it helps to appreciate why the lambda CDM model has been held in such high regard. It is built from observations of the cosmic microwave background, large-scale galaxy surveys, and measurements of the overall content of the universe, such as the amounts of visible matter, and dark energy. This model says that the cosmos is made up of roughly 5% ordinary matter, the kind that makes up stars, planets, and people. Then there's about 27% dark matter, an invisible ingredient detected by its gravitational effects but which has never been directly seen in the lab. The last piece is the mysterious dark energy, around 68%, which is responsible for speeding up the universe's expansion over time. What makes this model powerful is that it predicts how the small, lumpy regions in the early universe will grow under gravity over billions of years. Tiny ripples form denser knots of matter, and those knots act as the birthplaces for galaxies. The lambda CDM model says this process is gradual and hierarchical, which means that small objects merge over time to build larger one-say kind of cosmic stacking up that continues for billions of years. The model also says galaxies should start as irregular, patchy clumps and only slowly build up enough mass, dust, and heavy elements to look like the big, bright galaxies we see today. So when JWST sees a massive, mature galaxy only about 300 million years after the Big Bang, it doesn't match up. In the lambda CDM timeline, everything about the early universe creates bottlenecks. Right after the cosmic microwave background forms, the universe is too hot and dense for stars to form. After it cools, star formation has to fight against the tendencies of dark energy to stretch everything out, and against feedback from exploding stars, which can blow gas away. Then, the process of building up a large galaxy should require merging many smaller pieces, which is time-consuming because the objects have to find each other and combine without being torn apart. This new observation is creating a tension in the field because those who run computer simulations based on lambda CDM are finding it hard to make galaxies as massive and mature as the JWST discovery, especially at such an early date. Some teams have tried tweaking how quickly gas cools and collapses, or how star formation ignites in especially dense pockets of matter. Others have adjusted the rules controlling feedback, how much the first stars and supernovas heat and stir up their neighborhoods. But despite a lot of flexibility, these adjustments have limits, too much tinkering in one direction, and you end up with predictions that don't fit the actual distribution and mass of galaxies observed at later times in the universe. Too little stretching of the model, and it cannot account for the extreme objects spotted in the very early snapshots. A major source of challenge here is the idea of hierarchical growth. Lambda CDM builds all cosmic structures from the bottom up. Galaxies don't just pop into existence fully formed. They build piece by piece, with small objects forming first, combining gradually, and growing into the giants we see in today's universe. This slow stacking up is strongly supported by studies of galaxies in the more recent observable universe, where we do see evidence of mergers and accretion events written into the star's motions and chemical fingerprints. The trouble is, if this slow process dominates in the earliest times, it should simply be impossible to get a pure, mature, massive galaxy so quickly as JWST now reveals. The role of dark matter in this equation is particularly interesting. Cold dark matter is a key part of the model, shaping the gravitational scaffolding on which gas and stars collect. In lambda CDM, Dark matter acts as the invisible backbone, guiding all the visible matter in the universe into clumps and filaments. These filaments are thought to be where gas cools and settles, letting stars and galaxies grow. If there's something missing or misunderstood in how dark matter behaves, or interacts specially under the hot, dense conditions of the first few 100 million years, it could throw off all the timelines. Some scientists have started to wonder if dark matter clumps together more efficiently or somehow accelerates galaxy formation early on. Others have speculated about the properties of dark matter itself, wondering if alternative forms like warm or self-interacting dark matter could better match early observations. That said, these ideas run up against all the other evidence showing that cold dark matter works well across much of the observable universe. Feedback is also a sticking point. The Lambda CDM model relies on feedback from early stars and black holes to explain why galaxy formation is usually inefficient, meaning that only a small portion of the gas in a given region actually gets turned into stars. Supernovas, for instance, can blow gas out of tiny proto-galaxies, making it harder for the next generation of stars to form. In simulations, tweaking the amount, strength, or timing of that feedback changes how quickly galaxies can grow their mass and look mature. If feedback was less destructive, or worked differently in especially dense areas, or for early massive stars, it might allow for galaxies like the one the JWST found to develop quickly. Still, scientists have to balance that idea with all the other galaxies seen today, so the change can't create bigger problems elsewhere in the timeline. Another challenge for the standard model comes in the form of chemical enrichment in galaxies. Lambda CDM naturally leads to an expectation that the earliest galaxies will be mostly made up of hydrogen and helium, because those are the only elements formed directly during the Big Bang. Only after the first generations of stars live and die can heavier elements build up in the gas clouds, leading to the creation of later stars with more complex chemistries. But JWST's detailed look at some early galaxies shows chemical fingerprints that indicate multiple rounds of star formation, and possibly even the presence of heavier elements like oxygen or carbon. If this result holds up for more early galaxies, it means the first stages of cosmic evolution may have operated much more quickly than previously believed. Scientists working in cosmology are also very aware of the possibility that a few anomalous discoveries can spark major changes. For now, though, the evidence from JWST is pushing the community to reconsider just how rigid or flexible the standard model needs to be. Some teams are running new calculations, with slightly different parameters changing the cooling time of gas, or how fast dark matter aggregate testo see if these tweaks can close the gap. Others are getting more adventurous, trying out types of dark matter that act differently at small scales or in dense regions. But every change has consequences, since the Lambda CDM model is tightly bound not just by what happens in the early universe, but also by what is seen at every stage along the cosmic timeline, right down to today. One particular strategy cosmologists are taking now is to gather more data, not just with spectra and images of these early galaxies, but also by looking for patterns in how many mature galaxies appear at every redshift or distance. If JWST keeps finding many massive, mature galaxies way earlier than the model allows, it becomes harder and harder to explain them away as statistical outliers or rare coincidences. Eventually, the model would have to be rethought at a more fundamental level, possibly even requiring new physics or changes in the very nature of dark matter, star formation, or even cosmic expansion. It's also important to point out that the Lambda CDM model has weathered challenges before. Past surprises, like the discovery of dark energy in the late 1990s, or the detection of galaxies much earlier than expected in Hubble data, led to refinements but not a wholesale rejection of the standard framework. What's more, the model has been impressively robust at describing so many observed features, from the cosmic background radiation to how clusters move and interact across vast distances. That makes the tension from JWST discoveries all the more significant. If these new galaxies really do break the model, it would signal the need for a big shift in thinking. Cosmologists are not just looking to tweak numbers or adjust a few knobs. They are open to the idea that some core assumption might be off, like how feedback loops work, or how fast cooling can proceed in the highest density areas of the universe's first clumps. Other theories propose that maybe what astronomers see is boosted by unusual events, like rapid early black hole growth, gravitational lensing that makes galaxies look brighter and bigger than they really are, or some unrecognized bias in observation technique. But the more careful the checks, and the more examples JWST finds, the less likely it seems that these are just oddballs made by chance. The possibility that the properties of dark matter or the fundamental ingredients of the universe itself are different than current assumptions brings a sense of excitement mixed with caution. It is not often that astronomical discoveries point to a potential overhaul of the standard model, but responsible scientists want to see repeatable, clear results. They are demanding more evidence before accepting any big leaps in the understanding of how everything fits together. Moving forward, researchers know that modifying the Lambda CDM model will not be a simple process. It involves collaboration between observers, theorists, and experimenters groups that build telescopes, run computer models, and design laboratory experiments for things like particle properties and gravitational tests. If more of these extraordinary galaxies keep showing up, theorists may need to adjust assumptions about the earliest star formation, rethink the amount or behavior of dark matter, or even propose new laws for how energy and matter interacted in extreme conditions. Some of the new directions under consideration include the role of exotic particles, unaccounted for phase changes in early cosmic material, or unknown feedback mechanisms. The practical consequence of all these discussions is that scientists are gearing up for an era of testing and retesting the very basics of cosmic evolution. That means running hundreds of thousands of new computer simulations, comparing predictions to JWST's results, and asking whether small changes in the ingredients make major impacts across the universe's timeline. It also means preparing for results from other upcoming observatories, which might add crucial pieces of the puzzle here, suggest that the early, massive, mature galaxy seen by JWST is truly just the tip of the iceberg. In the meantime, there is a healthy sense of skepticism and excitement in the field. On the one hand, astronomers do not want to throw away a model that explains so much with a single surprising result. On the other hand, they do not ignore new facts, especially ones as striking as a galaxy that predates nearly all expectations for its size and maturity. The goal is to find that middle path, where models are adjusted based on reality, but not tossed out unless repeated. Consistent results demand it. As JWST continues to offer up clearer, farther, and more detailed glimpses into the universe's infancy, cosmology is entering a truly interesting phase where every new discovery has the potential to reshape core concepts about what the universe is, how it grows, and what undiscovered wonders still wait in the dark, silent depths of space. Scientists are now asking themselves what could explain such rapid galaxy growth and maturity so soon after the universe's beginning. The discovery of ancient, unexpectedly developed galaxies is not just about pushing the limits of what we thought possible. It's forcing researchers to reconsider how galaxies form, how stars ignite, and how these processes might have operated very differently in the early universe compared to now. The puzzle begins with the basics, which involve huge clouds of hydrogen and helium gas starting to collapse under gravity. In the young universe, you might expect this collapse to be relatively slow because the gas would still be extremely hot and not easily able to cool down and condense. Cooling is a critical process because it allows gas to lose energy and squeeze together enough for gravity to take over and trigger star formation. In the standard view, dense regions of gas only start to collapse and form stars once cooling gets efficient. These first stars, called population 3 stars, would be extremely massive, hot, and short-lived, blowing out a lot of energy and enriching their local environments with heavier elements when they exploded. This should make further rounds of star formation more likely later on, as enriched gas cools much faster than pure hydrogen and helium. But the timeline that everyone expected was stretched over hundreds of millions of years. The surprisingly mature galaxies seen by the James Webb Space Telescope appear to compress all of this activity into a much tighter window. One leading idea to explain what JWST is revealing is that star formation in the early universe was simply much more efficient than anyone predicted. Efficiency here means that a far larger fraction of the available gas quickly ended up in stars, without as much being blown away or left behind. There could be several reasons for this high efficiency. The earliest cosmic structures might have formed in especially dense regions of the universe, or gas clouds might have cooled quickly due to higher densities or unknown processes, leading to runaway star formation right from the start. Another possibility is that feedback energy released from the first stars in the form of light, wind, and supernova explosions may have been different than expected, allowing more gas to keep collapsing and spawning new stars. Researchers are considering that the mechanisms governing gas cooling could have acted faster under conditions of the early universe. For example, first-generation stars could have produced large amounts of ultraviolet radiation and early forms of dust, both of which might change the chemistry and cooling of nearby gas clouds. When cooling becomes easier, a region can produce stars more rapidly, and the cloud of gas collapses into a galaxy that is massive and bright much sooner than models predicted. Another explanation being explored is that young galaxies may have grown rapidly by merging with many smaller galaxies in quick succession. The early universe was a crowded place at small scales, so collisions between galactic fragments might have been much more common and violent than later on. Each merger could trigger intense periods of star formation, known as starbursts, quickly building up both mass and structural complexity. Multiple mergers in the first few 100 million years could explain how a galaxy got so big, dense, and organized in such a short time. The evidence of these mergers can sometimes be found in the shapes, orientations, and velocities of stars within the galaxy, or in the presence of multiple distinct star populations. There is also the scenario where cosmic material, meaning the gas and dust that gets recycled as stars form, die, and explode as supernovae was recycled more swiftly than anyone realized. If the first rounds of stars lived and died fast, they would have released a lot of heavier elements into their host galaxy early, kickstarting the next generation of star formation. With each rapid cycle, the galaxy becomes more mature and enriched, developing structural features, internal organization, and even possibly the beginnings of new elements like carbon, oxygen, or nitrogen. These processes could happen repeatedly and much faster than previously measured or simulated. All these hypotheses point toward the need to rethink how the first rounds of star formation and galaxy assembly happened in an environment with almost no metals and with much higher overall densities than today. Metals, in astronomy, mean any element heavier than hydrogen and helium, and they are important because metal-enriched gas cools much faster and can form stars more effectively. Early universe gas, having yet to be enriched by stars, should have cooled slowly. If metals built up much faster than models allow, or if dust developed rapidly after the first supernovae, it could have turned star formation into a runaway chain reaction. Some researchers are revisiting the potential effects of black holes, which might have formed very early and grown quickly in the cores of young galaxies. As black holes accrete gas and dust, they give off intense radiation that can both heat up the surrounding gas-slowing new star formation in some regions and compress nearby clouds, sparking starbursts in others. If these black holes grew fast enough, it's possible they contributed to the rapid construction of mature galactic cores. Observations of supermassive black holes in incredibly young galaxies hint that these processes could have been more common or more influential in shaping early galaxies than previously thought. Computer simulations are now being redesigned to test all these theories against the new evidence coming in from JWST. Simulating galaxy formation is a massive computational challenge because you have to model gravity, gas cooling, star formation, feedback from supernovas and black holes, mergers, chemical enrichment, and sometimes interactions with dark matter all at once. Earlier simulations, based on the accepted timelines, rarely produced galaxies as big and mature as those now observed. Teams are updating their codes with different cooling rates, higher star formation efficiencies, and more frequent mergers to see if those changes produce populations more in line with JWST's findings. Star formation itself might work differently in environments that are denser or more varied than assumed. For example, some suggest that if early gas clouds collided more often or collapsed under stronger gravitational forces, the resulting star clusters could be larger, triggering further rapid growth. Other scientists are considering whether cosmic rays, magnetic fields, or exotic particles played a bigger role at the beginning, affecting cooling or the structure of the gas in ways not captured in current theories. Naturally, astronomers are cautious, asking if there could be new sources of error or unrecognized effects in analyzing such distant and faint light. But as JWST continues to collect more data, and as other telescopes add their confirmations, the evidence for early, mature, and massive galaxies is getting stronger. The deeper researchers look, the more they find hints that the universe was a surprisingly dynamic and efficient factory of stars and galaxies in its first few 100 million years. With these discoveries, people must also consider the feedback processes from supernovas and young hot stars in a different light. It was previously believed that feedback worked to slow things down, driving out gas and limiting further star formation until more gas cooled and returned. If instead the situation was such that feedback sometimes promoted further star birth or was less destructive in certain regions, whole galaxies could continue building out and maturing much faster. This is an important subtlety, as not all feedback effects have to be purely negative. Some supernovae enrich the surrounding gas with metals, while also compressing nearby gas clouds, creating fertile ground for more stars. There is also the complexity of cosmic environment. In denser patches of the early universe, where the web of dark matter filaments was especially thick, gas may have fallen into galaxies more rapidly, feeding ongoing star formation and driving early assembly. If this preferential growth in some regions was more common than expected, our sample of known ancient galaxies could be biased towards those that happen to form in the busiest cosmic intersections. Another angle being taken involves looking at the universe's ultraviolet background, the general bath of light from the first stars and galaxies. If this background became strong enough, it could alter how gas clouds collapsed, either delaying or, surprisingly, sometimes accelerating star formation under specific conditions. Feedback from supermassive black holes, sometimes called active galactic nuclei, might produce powerful jets and winds that sweep through the whole galaxy, stirring up the gas and potentially triggering star formation away from the center. Evidence from later epochs suggests that black holes play an important regulatory role in galaxies, limiting star formation in massive systems. But it is possible that in the early universe, their influence was more mixed and sometimes even supportive. There's even the suggestion that our picture of the initial conditions of the universe could need an update. If there were larger fluctuations in density, or if conditions varied more across large regions than current models admit, some areas could see galaxies grow faster thanks to head starts from local overdensities. This relates directly to how the universe's first lumps came together after the Big Bang, as revealed in the cosmic microwave background radiation. As people dig into these questions, it becomes clear that making sense of early galaxy maturity requires everything from observers using JWST to theorists running huge simulations to work together and update the assumptions underlying their work. For decades, researchers understood star formation and galaxy assembly as long, gradual, hierarchical processes. And for many galaxies, that idea is still a strong match. But the exceptions, the ones breaking the rules, force the whole community to improve its understanding and potentially add entirely new pieces to the puzzle. Meanwhile, astronomers are also focused on better determining the ages of these galaxies. They analyze starlight to estimate the range of ages within each system, looking at the distribution of star masses, colors, and chemical fingerprints. If they find not just a few old stars but whole populations, that's yet more evidence for rapid early evolution. Precise measurement is tricky because the further away and older a galaxy is, the more stretched and dim its light. Still, technology is reaching levels where confident age dating is possible, and new spectroscopic surveys from JWST and future instruments will add clarity. Adding all of this together, the cosmology community is entering a period of energetic revision and exploration. Some projects now focus on mapping out the details of star formation efficiency. How much gas, under what density and temperature, becomes stars in different scenarios. Others look at feedback, both positive and negative, and simulate how different strengths and timings change the growth path for galaxies. Teams are rebuilding their cosmic simulations in light of this, including variations in how gas cools, how turbulence affects star clusters, and how quickly black holes might grow and influence their surroundings. What is clear is that the early universe was a place of great variety, and cosmic evolution may not follow just one script. The pattern revealed by JWST is nudging people to imagine early galaxies as more diverse, sluggish, and lumpy, some fast and organized depending on their local circumstances, feedback effects, and perhaps the types of stars and black holes they hosted. Rather than a single timeline for galaxy growth, there may have been many different tracks running in parallel, leading to the rich and sometimes surprising diversity we see in the young universe. To keep up with these findings, international teams are pooling resources, comparing results, and publishing a flood of new studies and computer models. The field is advancing quickly, with collaboration between observers, theorists, and experimenters who test how physics works under the most extreme cosmic conditions. As new discoveries keep coming, the overall picture deepens, and researchers find themselves not just adjusting the timeline but sometimes rewriting fundamental rules about how stars light up, how galaxies assemble, and how the universe turned from featureless gas into a cosmic city full of giant galaxies in record time. As the James Webb Space Telescope shows us more examples of ancient, mature, and massive galaxies, researchers are embracing the chance to adapt and refine their understanding of cosmic beginnings. No model lasts forever without revision, and each extraordinary find becomes a touchstone for improvement. The early universe is turning out to be a more energetic and surprising place than many astronomers ever dared to expect, and the adventure of rewriting cosmic history is just gaining momentum. All these breakthroughs in our understanding of the early universe and the big surprises from ancient massive galaxies wouldn't be possible without the game-changing tools astronomers now have. Among them, the James Webb Space Telescope stands out as one of the most advanced machines ever built for looking deep into cosmic history. Even before its launch, people in the astronomy community were excited about what it might find, because it was designed from the ground up to answer questions and probe mysteries that older telescopes simply couldn't touch. The James Webb Space Telescope's capabilities aren't just a step up from its predecessors, they are at a whole new level, especially when it comes to peering back into the earliest times after the Big Bang. The actual design choices made for the James Webb Space Telescope all address the major technical hurdles in observing the young universe. For starters, astronomers must look at objects whose light is not only faint, but stretched into the infrared part of the spectrum due to the constant expansion of the universe. What this means is, light that once left an early galaxy as visible or ultraviolet radiation is now arriving at Earth as faint infrared signals, after traveling for over 13 billion years. Most other telescopes, including the famous Hubble Space Telescope, are mostly sensitive to visible and near-infrared light, which limits how far back in time they can see. The James Webb Space Telescope, in contrast, can collect and analyze light in the mid-infrared range, where much of the earliest cosmic information is found. A big reason the James Webb Space Telescope is so powerful comes down to its main mirror, which is massive compared to any other space telescope. The mirror is about 6.5 meters across, more than twice the size of Hubble's. More surface area means more light collected, and for astronomers trying to detect the faint glimmers from the universe's earliest objects, every bit of light matters. That size allows it to detect much dimmer galaxies than what was possible before, making it basically an essential tool for seeing back to when the universe was just a few 100 million years old. Another critical factor is location. The James Webb Space Telescope doesn't orbit close to Earth like Hubble does. Instead, it sits about 1.5 million kilometers away at what's called the second Lagrange point, or Li2. In this spot, the telescope gets a stable environment shielded from the heat and stray light from both the Earth and the Sun. Any additional heat or light would create background noise and drown out the faint signals from faraway galaxies. To keep itself cold, the telescope has a special multi-layer sun shield, about as big as a tennis court, that blocks heat and light, so the instruments inside can chill near negative 233 degrees Celsius. This extremely low operating temperature is a must for capturing those faint infrared signals without contamination from the telescope's own equipment. On board the James Webb Space Telescope are 4 key scientific instruments, each built to do different but complementary jobs. There's NIRCam, the near-infrared camera, which is especially good at picking up red-shifted light from distant stars and galaxies. There's also NIRSpec, the near-infrared spectrograph, which breaks incoming infrared light into its component wavelengths, letting scientists analyze the chemical composition, temperature, and movement of faraway objects. The third is MIRI, the mid-infrared instrument, which extends the telescope's reach deeper into the infrared and is crucial for studying even cooler or dustier structures in very young galaxies. Lastly, there's the fine guidance sensor, along with a near-infrared imager and slitless spectrograph, the FGS and NIRIS, that help pinpoint targets and split light for high-precision studies. When astronomers first used the James Webb Space Telescope to look at deep space, it was like suddenly having a time machine that could show the universe as it was close to the beginning. Because light takes time to travel, looking farther means looking into the past. For the first time, scientists could target galaxies thought to have formed just 200 or 300 million years after the Big Bang. These galaxies are so far away, and their light so stretched and faint, that only a telescope with the size, sensitivity, and ice-cold operating temperature of the James Webb could actually spot them, let alone resolve any details. What the James Webb Space Telescope revealed was not only a surprise, it was a complete shift. Scientists expected to find small, dim, relatively unremarkable early galaxies, maybe just glimmers of starlight collected in irregular lumps. Instead, they found some galaxies that looked far more mature, larger, and brighter than the prevailing theories had allowed. What's more, Webb provided actual data on the mass, structure, and even the makeup of these galaxies, thanks to its powerful suite of instruments breaking down their faint infrared light. With its ability to do high-resolution spectroscopy, the James Webb Space Telescope can not only see a distant galaxy, but also determine what elements are present in that galaxy, how old some of its stars are, and how quickly stars are forming there. The telescope's images are so fine that for certain galaxies, researchers can see hints of structure like clumps, disks, or dense corazon systems more than 13 billion light-years away. Before Webb, this was completely out of reach. The reason analyzing the spectrum matters so much is that it turns spots of light into real physical objects with detailed histories. By breaking a galaxy's light into its spectrum, researchers can spot the fingerprints of hydrogen, helium, and even heavier elements like oxygen, carbon, or iron. They can tell how enriched with metals a galaxy's gas is, which is a big clue about how many rounds of star formation have already taken place. If a very young galaxy has a lot of these heavier elements, it means several generations of stars must have lived and exploded as supernovas in rapid succession, turning a primordial gas cloud into something much more complex. And it's not just galaxies that the James Webb Space Telescope can examine. The suite of instruments on board means astronomers can pick out faint, cold dust clouds, infant stars, forming planetary systems, and early clusters of galaxies. All of these objects leave subtle marks in the infrared light they emit or absorb, and Webb's detectors are tuned to pick up those subtle differences. In practice, this means that even previously invisible objects, so faint and distant that no other telescope could find them, can now be detected and studied. An additional, huge technological leap is in the sheer field of view and data collecting power. The James Webb Space Telescope can study thousands of galaxies at once in its deepest survey modes. Each exposure covers a patch of sky, with the potential to hold dozens or hundreds of never-before-seen galaxies. As more survey fields are imaged and analyzed, the chances go up for finding more of these puzzling, mature galaxies, whose existence challenges what everyone thought was possible so soon after the Big Bang. The instruments are also designed to sort out the faintest signals from overwhelming background light. They achieve this by deploying advanced detectors with low read noise, careful shielding, and smart software that spots and rejects cosmic rays, instrument glitches, or random hot pixels. These details might sound minor, but when you're pushing to the extremistring to see light that left its source over 13 billion years ago, every technical advantage is essential. The telescope's flexibility also helps. The design allows astronomers to switch between imaging full fields and drilling into individual objects for deep, detailed spectra. A team might scan for the most distant, high-redshift galaxies, then zero in on a shortlist for closer analysis, pulling out information about their internal dynamics, chemical makeup, and star formation activity. Scientists can cross-match Webb's discoveries with earlier data from Hubble or ground-based observatories, pulling out even more clues about how these ancient galaxies came together. Moreover, James Webb's location at Leto and its ability to stay cold and stable for years at a time means researchers can keep returning to the same targets across multiple observing seasons. This lets them see changes in supernova activity or galaxy growth, map out the spread of new elements, or catch the faint flicker of stars coming and going in faraway systems. Long, uninterrupted observations, free from Earth's atmospheric glow, boost the signal-to-noise level and provide astronomers with data of a quality never reached from the ground. Considering all this, it's easy to see why the discoveries have moved so quickly. Shortly after getting its first clear images, the telescope started delivering results that challenged established science. Teams searching the deepest fields, like the JWST Advanced Deep Extragalactic Survey, found galaxies at mind-bogglingly high redshifts. These galaxies, whose light was sent out when the universe was a few 100 million years old, popped up in numbers and with properties no models had forecast. And the pace of discovery hasn't slowed. As more data pours in, scientists are already finding a population of ancient galaxies with masses, brightness, and structural clues that suggest that our basic assumptions about galaxy formation need another look. The James Webb Space Telescope also offers huge improvements for measuring distances accurately in the very distant universe. Its spectrographs can determine redshifts with more precision than previous tools, and its ultra-sensitive detectors can pick up signatures from faint emission lines caused by elements in the gas between stars. These measurements help lock down exactly how far away a galaxy is, and, by extension, how soon after the Big Bang it must have formed. The ability to collect both images and spectra simultaneously on dozens of objects at once is pushing cosmic distance charts to unprecedented detail. Researchers running simulations and constructing theories have found the telescope's steady output of new data both invigorating and demanding. Every new JWST discovery feeds back into updated computer models, which must be tested against what is actually seen. If a simulation produces too few massive early galaxies, or struggles to generate young but chemically enriched systems, theorists go back to their assumptions. The result is a more collaborative, fast-paced scrutiny and revision process within the astronomy community. So, in a short time, the James Webb Space Telescope has done more than simply amaze people with beautiful deep sky photographs. It is changing textbooks and lecture slides, forcing scientists to revisit old rules for how galaxies grow, how elements build up, and what the very first few 100 million years of the universe were really like. It has let researchers put old theories to the test on new and unfamiliar ground, seeing farther, deeper, and in more detail than anyone thought possible, even a decade ago. The world is still only at the beginning of what JWST can do with years of science ahead. With thousands of scientists around the world requesting to use the telescope's power for all sorts of projects, not just galaxy formation, but star birth, black holes, planetary system studies, and more, the flow of discoveries is likely to keep growing. As more fields are observed and new processing techniques are developed to sift through the deluge of data, surprises will keep coming, and every new, impossible galaxy or disorderly structure at the edge of the observable universe will be a further piece in the puzzle, reshaping not only how we picture the first galaxies, but also how the universe itself went from the afterglow of the Big Bang to the complex web of matter and light we see today. As new data keeps rolling in and new tools keep raising the bar for what's possible, astronomers are starting to realize that spotting a mature and massive galaxy so early is not just to surprise it, raises a whole set of deep questions about the fundamental rules that governed the early universe. Now, attention is turning not only to how galaxies formed, but also to the actual physics of the young universe itself. This is pushing experts to dig into what matter and energy were really doing during those first hundreds of millions of years after the Big Bang. The early universe was not just a scaled-down version of what we see today. It was a time with its own unique rules, dominated by intense heat, density, and forces that might have played out in unexpected ways when compared to the cosmos as it is in the present. One of the central mysteries is how matter behaved under these special conditions. In the first few 100,000 years after the Big Bang, the universe was so hot and thick with particles that atoms themselves could not even form. When things finally cooled down enough for protons and electrons to bind together and make hydrogen, the universe entered a period called the Cosmic Dark Ages. No stars existed, and matter drifted as a diffuse soup. The first structure clumps of dark matter and gas started to form as gravity worked slowly but relentlessly, pulling things together. Yet, despite all this, seeing intricate galaxies arise barely a few 100 million years later means some processes worked much faster or more efficiently than anyone had guessed. The makeup of the early universe was simple, almost entirely hydrogen and helium, with tiny traces of other light elements. Heavy elements, known as metals in astronomy, only started to appear after the first stars ran through their lives and blew up as supernovae. That means the ways gas cooled, collapsed, and formed new stars was tied directly to chemistry. Cold gas makes it easier to bundle up and form stars, but pure hydrogen and helium cool slowly. There is a possibility that unknown mechanisms or overlooked reactions made cooling easier, or perhaps that the chemistry involved was more complex due to interactions no one has yet factored in. The addition of even a small amount of dust or pollution from the first stars could dramatically speed things up. Another layer to the mystery is the behavior of dark matter in the universe's early epochs. As far as scientists know right now, dark matter does not interact with light or regular matter, except through gravity, but it is essential for forming structure. The lambda-cold dark matter model is built on the idea that slow-moving dark matter acts as the gravitational glue that helps normal matter gather into galaxies. Still, there's a debate on whether dark matter could have acted differently long ago, maybe forming tighter clumps or collapsing faster, which could have set the stage for rapid galaxy growth. The rates at which gravity, cooling, and star formation happened would also be shaped by the density of the universe at the time. When you look at the young cosmos, it was much more compact. Galaxies could merge or pull on each other more easily, and gas might have crashed into itself more often, all helping to speed up the formation process. There's a big effort now to study whether this cosmic crowding by itself explains how some galaxies became so massive and mature, or if additional unknown forces were at play. On top of gravity and chemistry, there could be new physics in play processes, or particles that don't matter much today, but made a big difference when the universe was young and hot. Some experts have proposed that particles predicted by theories beyond today's standard model of particle physics, like axions or sterile neutrinos, might have affected how matter cooled or how galaxies assembled. There's also curiosity about whether the properties of dark energy, which pushes the universe to expand faster, might have shifted during the first billion years of cosmic history. Cosmic reionization is another part of the puzzle. This is the era when the first stars and galaxies put out so much energetic light that it broke apart hydrogen atoms floating in space, changing the game for how future stars could form and how galaxies could grow. Determining when and how quickly reionization happened is crucial, and the James Webb Space Telescope is already helping to zero in on those answers. Reionization affects not just the visibility of ancient galaxies, but also their ability to keep growing if it came earlier or progressed faster. That could have given some galaxies a head start. Astrophysicists are also studying whether the behavior of clouds and filaments of gas in and around galaxies changed as the universe's temperature dropped. Maybe flows of gas into early galaxies were less disrupted by starlight and winds than in later times. Or maybe turbulence and magnetic fields funneled more material into these structures. There's a renewed interest in the complex roles these environmental effects play, as they might turn out to be deciding factors in determining which galaxies could mature quickly. Powerful black holes are another part of the equation. If black holes formed early and accreted gas at rapid rates, their powerful radiation and jets could change the conditions around developing galaxies. Instead of just blocking star formations, most people once thought it now seems plausible that these energetic outflows could also compress clouds and trigger more starbirth, essentially acting as both a brake and an accelerator, depending on the situation. This dual influence complicates models, but it also provides new ways to explain the fast maturity shown in some of the earliest galaxies observed. Particle physicists are also becoming increasingly interested, since the rules that shaped the early universe offer one of the best chances to spot new physics beyond what is seen in laboratories. There is talk of searching for faint imprints in the cosmic microwave background or in the distribution of the oldest galaxies, hoping to find evidence for exotic particles or forces that haven't been detected directly. The early universe, with its unique blend of extreme temperature, density, and rapid change, might have let some phenomena stand out in ways impossible to detect under current-day conditions. Alternative theories about dark matter and cosmic structure are getting fresh attention too. Some researchers are experimenting with ideas like self-interacting dark matter, which could help explain how mass came together so quickly and why some galaxies appear more mature than expected. Others are looking at the effects of warm dark matter, which might smooth out small structures but also speed up large-scale assembly in its own way. Each of these models leaves clues in how galaxies are spread out, how massive they are, and how their internal structures form. All of these angles chemistry, gravity, dark matter, new particles, reionization, and black holes are now being woven into the next generation of computer simulations. Teams around the world are racing to write more accurate, more detailed models that can track billions of particles, clouds, and subatomic events from the earliest times up to today. These enormous computational projects, sometimes running on supercomputers for weeks at a time, let physicists tweak the rules and see how galaxies form under different assumptions. Every time the simulations match what the telescopes see, confidence grows. Every time they fail, it points to something missing in the theory. At the same time, astronomers are grinding through massive catalogues of new galaxies to hunt for patterns or exceptions. They measure things like the ratios of elements, the masses of galaxies, and the rates at which new stars are forming. The goal is to spot trends that either support the current understanding or demand something new. For example, if every ancient massive galaxy has unusually high metal content that hints at a rapid cycle of star birth and death no one had expected. If their sizes and structures are all over the map, maybe the environment or random chance played a bigger role than anyone realized. Observational cosmology is changing as a result. For decades, most discoveries supported the broad strokes of the lambda cold dark matter model. Now, with every new data release from JWST, the early universe looks like a place of both order and surprise. The growing list of ancient, developed galaxies, enigmatic black holes, and chemically rich stars is pressuring theorists to dig deeper, not just to fine-tune parameters, but to ask if there are fundamental rules overlooked. A huge part of this detective work is making sure the interpretations of the data are accurate. Researchers cross-check redshift calculations, check for contamination from nearer objects, and debate whether gravitational lensing is making galaxies appear more massive or brighter than they are. They're careful to rule out simple errors before jumping to radical conclusions. It's a process where curiosity and skepticism go hand in hand, aiming to build the most solid possible picture of those earliest cosmic times. With all eyes on the distant universe, new ground-based observatories and future space missions are lined up to test results from JWST and push the limits even farther. Radio telescopes, X-ray observatories, and planned next-generation infrared space telescopes will each add their unique perspective, letting researchers cross-check discoveries and sharpen their understanding of early universe physics. As more and more galaxies pop up in the first few 100 million years after the Big Bang, scientists will have the statistical power to pin down whether something fundamental is really being missed. Meanwhile, the collaboration between astronomers and particle physicists is growing closer. As observations reach deeper and the need for new ideas grows, experimentalists in labs are hunting for signs of the particles and forces that might have played a part when everything was just getting started. Underground facilities look for dark matter, Accelerators like the Large Hadron Collider seek out hints of new particles. All the while, telescopes keep gathering cosmic signals that just might hold the answers. It's clear that the physics of the early universe is not a closed book. The processes that unfolded in the first hundreds of millions of years after the Big Bang continue to surprise even seasoned experts, inviting both careful testing and bold new speculation. The ultimate goal is to find the missing pieces, so theories not only fit what happens in the present, but actually match what is being seen from the universe at its youngest stages. A single, unexpected discovery, a massive, mature galaxy, or an unusually old black hole, has the power to shift what is considered possible. As long as telescopes like JWST and their successors keep looking deeper and with finer detail, every new result will help answer the mystery of what made the early universe so efficient, so fast-moving, and so full of surprises. The journey is pushing science to new frontiers, inviting everyone to rethink not just how galaxies grow, but what kind of laws were in charge right after everything began. The answers may come not in a single leap, but step by step, as observation, theory, and experiment catch up to what the cosmic past is actually showing us. All these clues about the strange and energetic physics of the early universe put a spotlight on another huge idea that's getting a fresh look: what the discovery of a mature, massive galaxy just a few 100 million years after the Big Bang means for our understanding of the Big Bang itself, and for the whole story of how the universe went from nothing to the sprawling and organized cosmos we see now. For decades, scientists have relied on the idea that the universe started with a hot, dense, featureless state, and that after the Big Bang there was a long, dark, quiet interval before anything as complex as a galaxy could even begin to appear. Now, data from the James Webb Space Telescope are showing a sky that is much busier and more structured, much sooner than expected. That shakes up key chapters in our timeline of cosmic events. One of the big pillars of Big Bang theory is the idea that after the initial bang, the universe expanded and cooled so rapidly that atoms couldn't form right away. First came an era when everything was basically a free-floating plasma of electrons and protons. Hundreds of thousands of years later, cooling finally let electrons settle into orbits around protons, making the first neutral hydrogen atoms. This era is called recombination. That created the cosmic microwave background, the oldest light we can observe, which astronomers have mapped with enormous detail over the years. But even after this, for nearly 100 million years or more, scientists thought the universe was a very dark place. There were no stars, no bright objects, and essentially just clouds of invisible gas and slowly growing threads of dark matter. This cosmic dark age was supposed to end gradually, as the first stars finally lit up, perhaps 100 or 200 million years after the Big Bang. Those early stars, grouped in tiny, primitive galaxies, would slowly fill the universe with light and start fusing heavier elements, eventually triggering processes that made bigger galaxies and more complex structures possible. So, imagine the surprise when the James Webb Space Telescope identified mature galaxies containing stars, dust, heavier elements, and clear signs of ongoing star formation already, glowing brightly just 300 million years after the Big Bang. That's not just a question of spotting isolated bright dots here and there. It's evidence that the universe's cosmic dawn was in many ways more advanced, more dynamic, and perhaps even more crowded than anyone had thought. It's like hearing music in a room you had believed was still silent. The presence of these galaxies so soon after the start pushes all of science's models of the cosmic timeline, especially when it comes to how quickly matter organized itself and lit up the sky. This calls for a closer look at the so-called epoch of reionization, which is one of the most important parts of cosmic history. This is the period when ultraviolet light from the first stars and galaxies was energetic enough to rip electrons off hydrogen atoms throughout the universe, turning the intergalactic environment from a neutral state into an ionized, glowing sea. Understanding when and how this happened is at the heart of mapping cosmic dawn, the time when darkness truly gave way to light. Previously, models based on the amount of distant light and the properties of the cosmic microwave background suggested that this reionization happened slowly and was probably not complete until about 800 million or even 1 billion years after the Big Bang. But the sight of already enriched, organized galaxies shining at 300 million years means that massive bursts of star formation and organization were underway almost from the very start. This pushes the whole turning on process to a much earlier date, meaning the universe was assembling and lighting up far faster than expected. As more such galaxies are found, there's strong pressure to revise the details of when the earliest stars and galaxies appeared and admit that the first bright era came much sooner. That has a ripple effect on how scientists think about the chemistry and evolution of the universe too. For heavy elements to show up in these early galaxies, at least one generation of stars must have formed, lived out their lives, and exploded as supernovae. That means cycles of starbirth and death happened with breathtaking speed. The universe wasn't just making stars, it was recycling material and shaping itself into denser, more complex galaxies right away. That also means new types of stars and maybe even black holes could have appeared earlier than ever imagined. These discoveries are causing a lot of researchers to go back over the question of cosmic structure. How did matter go from a smooth, almost featureless spread to web-like networks, knots, and galaxies in such a short time? For this to happen, small differences in the density of the very early universe seen as slight temperature changes in the cosmic microwave background must have grown into bigger and bigger clumps. Gravity gathers matter, but it was thought that this was a slow grind, stretched out over long spans. With the James Webb Space Telescope showing otherwise, theorists are examining whether those early clumps grew faster, or if initial fluctuations were larger or more varied than previously calculated. Another impact of these discoveries is on the understanding of dark matter and its role in building early structures. If galaxies could become massive and mature so early, it might mean that dark matter formed denser halos more quickly than anyone thought, providing a kind of scaffolding for normal matter to collect and make the first stars. Alternatively, it could suggest that the nature of dark matter itself, the way it moves, clumps, or interacts, needs to be adjusted in our descriptions of the first stages of the universe. The signature of all these processes is etched into the light astronomers see. Light from these ancient galaxies is stretched by the expansion of the universe, so by the time it arrives, it provides a time capsule of conditions billions of years ago. By studying the colors and details in this light, scientists are piecing together not just the ages of these galaxies, but their contents and the pace of their assembly. JWST's ability to resolve both very faint and very distant objects is proving to be the key to rewriting our understanding of what the cosmic dawn era was actually like. Even the cosmic microwave background, one of the most important discoveries supporting the Big Bang model, is being re-examined with new eyes. Earlier, very detailed maps from missions like WMAP and Planck let cosmologists measure the universe's age, its overall contents, and even test the predictions for how the first tiny ripples should grow into galaxies. Now, with direct signs that galaxies and stars organize themselves faster than the baseline models predicted, some teams are checking for clues that might have been missed in the background, radiation to tatany tweaks, to temperature, hidden patterns, or other clues that dark matter, dark energy, or other unknown ingredients shifted the pace of structure formation in those earliest moments. Revising the cosmic timetable is more than an academic exercise. It forces big questions about everything that happened after the Big Bang. If the earliest galaxies formed sooner and the universe became transparent to starlight earlier, then the subsequent phases clusters, supermassive black holes, planet formation, and reionization may all have kicked off ahead of schedule. This helps explain some discoveries, like supermassive black holes found less than 1 billion years after the Big Bang, or surprisingly mature stellar populations in distant galaxies. These once mysterious objects fit much better into a universe where cosmic dawn was energetic and productive, instead of sleepy and gradual. The bigger story is that every detail of early galaxy formation, now visible in detail, speaks to how matter, gravity, and energy organize themselves. The process is tied up with both local conditions, like the density of gas and dark matter in certain areas, and with universe-wide effects, like expansion and cooling rates. If models now need updating, it could mean adjusting not just the small-scale recipes for making stars, but possibly the big-picture physics that drives the universe as a whole. One striking result is that astronomers are now carefully separating assumptions about when the Dark Ages ended, when stars switched on, and when galaxies got large enough to reorganize their neighborhoods. Light from these mature galaxies also helps map the timeline for when the intergalactic medium, the stuff between galaxies, was reionized and cleared up. That's important because it determines how other galaxies are seen and how energy traveled between different cosmic regions. By matching up how bright galaxies appear, how many stars they have, and how much heavy element content they display, researchers can pin down exactly when cosmic dawn started and how quickly it moved along. Intertwined with this is the story of star formation. For mature galaxies to appear so fast, star formation rates must have peaked much earlier and higher than models suggested. If the pace of star birth, stellar death, and chemical enrichment was much more intense, that means the universe was making and remaking itself at a fever pitch in its first few 100 million years. This goes back to feedback cycles, the efficiency of gas cooling, and the formation of giant clusters, all of which are now being updated in light of new findings. This early and unexpected maturity of cosmic structures has spurred a reanalysis of everything from the initial seeds of structure seen in the microwave background to the spread of the earliest heavy elements. It might mean that cosmic seeds were denser, or that feedback from the first supernovae was more constructive, or even that as yet unseen physical processes kicked in during those fast-moving early years. Every time astronomers find another ancient, rich galaxy, it's adding to the evidence that the story of the universe's first moments was anything but slow and steady. The discoveries from JWST also have scientists revisiting how the first black holes and early quasars, the brightest objects in the ancient universe, could form and grow so quickly. Maybe they started growing earlier, perhaps even before the first galaxies. Or maybe there are flaws in the measurements that date these objects. As of now, though, the signs point to a universe where everything from normal matter to black holes to complex chemistry got going in the fast lane. Current efforts focus on finding more galaxies at similar or even higher redshifts, which would provide a broader census of just how active and crowded the early universe really was. Each new detection feeds models and helps researchers test different versions of how cosmic history unfolded. For many scientists, this is an unprecedented moment, getting direct answers to questions that were simply off-limits for decades. The JWST has made it possible to connect the earliest light to the mature universe we see today, mapping every step from the Big Bang to the galaxies and stars filling the cosmos. The fact that impossible galaxies now keep showing up at the universe's energetic dawn has changed the focus for a whole generation of astronomers. The old boundaries between theory and observation are blurring as more objects are found and analyzed. All the new information points toward a model of the early universe that is richer, more productive, and more surprising than anyone working before JWST would have dared imagine. Throughout, a constant level of caution and peer review keeps these discoveries in check. Astronomers are careful, always seeking more observations, striving to measure each galaxy's distance, age, and composition as precisely as possible before rewriting any textbooks. But the evidence is growing that the Big Bang's aftermath was a high-speed, high-energy builder's playground. It was a time where stars and galaxies weren't just rare sparks in the dark, but were forming, dying, and reorganizing at a furious rate. In the end, all this means is that the Big Bang theory remains the best explanation for how the universe began, but its immediate aftermath now looks much livelier and more crowded than expected. The transition from the darkness of recombination to the full light of galaxies and stars happened not in slow motion, but as a dramatic burst of cosmic creation. As astronomers continue refining models and finding even more surprises, each detail uncovered about those first few 100 million years isn't just a curiosity, it's a vital piece in figuring out why the universe looks the way it does now, and just how quickly the cosmic dawn turned the universe from silence into a symphony of light and structure. Because the discoveries have changed the way researchers think about the Big Bang, and forced a rethink of the timeline for how quickly stars and galaxies formed. The next natural step is to ask if the mature, massive galaxy spotted by the James Webb Space Telescope is a rare outlier, or just the beginning of a bigger pattern. As soon as this first surprising galaxy was confirmed, astronomers worldwide started combing through the growing JWST archive, searching different survey fields and datasets for more examples. The question at the center of all this effort is simple but profound. Are there lots of these early, massive galaxies waiting to be found, or is the one just discovered a fluke? To try to answer that, teams are looking at the light from as many faint, distant sources as they can. Every time they spot a speck with the right kind of infrared signaturune that suggests it's coming from a galaxy that formed when the universe was just a few 100 million years old, they put it through a careful check. They look at how stretched its light is, using redshift, analyze its colors to see if it could really be as far away and as matured as it seems, and compare the size, shape, and brightness to theory. The process is time-consuming, but every new deep field gives them another chance to spot not just more mature galaxies, but also to compare how common or rare these large, developed structures actually are at extreme redshifts. The work is deliberate and careful, because mistaken identity is a serious risk when you're looking billions of light years away. Occasionally, something as simple as a foreground star or galaxy might mimic the appearance of an extremely old, bright object. Astronomers use various tricks, such as image sharpness, color filters, and even gravitational lensing data, to filter out these imposters. They also use follow-up studies, often with spectroscopy, to nail down redshifts and chemical signatures even more securely. This means that every claim of another impossible galaxy gets intense peer review and is often double-checked by different research groups using independent data. One important angle in the search for more of these galaxies is the statistical power that comes from bigger samples. When only one was known, all the focus was on explaining that single anomaly. But as researchers add more candidates, the search turns into something like a cosmic census. If impossible galaxies turn up in every deep field across different regions of the sky, and at different distances, then the evidence points to a much deeper issue with our models. The numbers matter because theories can handle an occasional outlier here and there. But if the early universe is routinely filled with galaxies that shouldn't exist yet, models will need much more than just a small tweak. Early results from JWST's surveys have already delivered some surprises. In certain fields, researchers have found more than one candidate for a mature, massive galaxy within the same cosmic era. Some are relatively compact, while others show extended structure or evidence for ongoing starbursts. Teams have even started spotting signs of early galaxy clusters, suggesting that big structures formed together not long after the first light. The diversity alone large, bright clumps alongside fainter, messier ones adds further weight to the idea that the early universe was more dynamic and diverse than anticipated. Astronomers don't stop at just counting the galaxies. They also look for patterns. For example, do these mature galaxies only turn up in regions where dark matter is expected to be denser, or in spots with higher cosmic web intersections? Are they spread randomly? Or do they follow the same kind of structures seen in the more recent universe? Patterns like this help narrow down whether the rapid growth of these objects was a widespread phenomenon or tied to very special environments. Beyond simply finding more mature galaxies, researchers analyze their individual properties. Each new object gets studied for its star formation rate, the age spread of its stars, its metallicity, a measure of how many heavy elements it contains, and even for clues about the presence of supermassive black holes at the core. Comparing these properties with predictions from cosmological models and simulations provides real-world feedback on how and how fast galaxies could be built under very different conditions from those seen today. One complication is that gravitational lensing sometimes magnifies faint, distant objects, making them easier to detect but also more difficult to interpret. When a background galaxy's light passes near a big mass like a cluster, it bends and can appear as an arc or a ring, sometimes even appearing brighter or larger than it really is. Astronomers must factor in the lensing effects very carefully to avoid overestimating the number or mass of these early galaxies. Thanks to JWST's sharp data and the ability to cross-check with other space and ground telescopes, lensing effects can be modeled and, in many cases, corrected. With more data coming in every month, astronomers are getting close to being able to estimate the rate at which big, mature galaxies appear at different moments in early cosmic history. This is where theory and observation collide. If the number of mature galaxies at, say, 400 million years post-bang is much higher than predicted, it means a major change in the way models treat star formation, gas cooling, feedback, or dark matter is on the table. On the other hand, if future deep surveys barely reveal any more, then there may be quirks or rare alignments that produce the first discoveries, and the foundational cosmological picture might still survive without major changes. The question of uniqueness was the first JWST galaxy a fluke, or the tip of a hidden iceberg, is central for the whole scientific field. If multiple independent teams, observing widely different sky locations, keep finding mature galaxies at the same ages and redshifts, the evidence quickly becomes overwhelming. If instead only a handful are ever found despite thousands of candidate objects being checked, the case for overturning the standard model gets weaker, but it still requires some fine-tuning to explain each outlier. Statistical robustness grows as more observing time is allocated to the most promising or surprising regions of the sky. JWST campaigns are organized in tiers, from ultra-deep fields that are exposed for many days to wider, shallower scans that maximize the number of unique galaxies detected. Both strategies have roles to play. Deep fields have the sensitivity necessary to spot very faint, ancient galaxies, while wide surveys show how common or rare these objects are over larger scales of the universe. The search doesn't happen in a vacuum either. Many teams combine data from JWST with earlier work from Hubble, or even radio and X-ray telescopes. Comparing galaxies across wavelengths provides crucial checks. A galaxy that looks massive and mature in the infrared should also have certain radio or X-ray properties if it is forging stars or harboring a black hole. This way, astronomers make sure that each candidate truly fits the picture of an impossible galaxy built in a hurry. Completing this bigger sample helps with more than just rewriting galaxy formation rules. Each new object provides a new laboratory to study not just the stars inside, but also the evolution of chemical elements, the growth of black holes, the development of galactic structure, and the properties of the cosmic environment in which it sits. Following up on these objects with JWST spectroscopy or high-resolution imaging helps nail down their distances, ages, and chemical fingerprints with more confidence each time. Some skeptics have pointed out that until every potential source of error is ruled out, caution is needed before declaring a revolution. That means triple-checking redshift estimates, accounting for the rare possibility of gravitationally lensed duplicates, and looking for subtle contaminants from the foreground. The community is fine-tuning tools and writing new software to improve image analysis, photometric redshift algorithms, and even the catalogs used to flag foreground or background confusion. When it comes to theory, each new mature galaxy offers a fresh test for models. Simulations are being updated in response to each new batch of real-world observations. Scientists alter the input physics, making gas cool faster, letting stars form more easily, testing new feedback models, or trying alternatives for dark matter's behavior. The more impossible galaxies are confirmed, the more pressure the simulations experience. If only a handful can be produced in a universe governed by the standard model, then it's a sign something fundamental needs to change in the way these codes handle cosmic growth in early times. International collaboration also helps speed up and check this process. Multiple observatories, research centers, and university groups are pooling their findings, organizing databases, and coordinating surveys, so no patch of sky or interesting result gets missed. Peer review is more than just a gatekeeping exercise. Here it's a global teamwork effort to make sure the discoveries are robust and the interpretations well-tested. Each time an ancient, impossible galaxy is found, the impact goes beyond the field of astronomy. It grabs attention in physics, computer science, and even philosophy, since big surprises in the cosmic record force everyone to reconsider how change unfolds across the universe. The race is on not just to tally up numbers, but to build full evolutionary stories for these galaxies, compare chemical histories, probe for black holes, and connect them with the web of dark matter and cosmic structure that underlies everything. Meanwhile, the search for more impossible galaxies is only accelerating. The JWST archive is growing at a massive rate, and with every data release, new teams are poring over faint signals and pushing the techniques for finding mature galaxies even further. Algorithms are getting more robust, machine learning is being used to flag weird or out-of-place objects, and software packages are continually refined to improve classification and measurement. Other space missions and ground surveys are starting to aim their own instruments at the most interesting JWST discoveries, checking for possible cross-confirmations or surprises in how these early galaxies shine across different bands of light. This big, coordinated approach is how science builds confidence and makes lasting changes to models. The future for this kind of work is bright. As JWST keeps going, and next-generation instruments like the Roman Space Telescope or the European Space Agency's Euclid mission come online, coverage of the ancient universe will only get broader and more detailed. Every new galaxy found and analyzed makes it clearer whether we are facing a cosmic revolution or just dealing with extremely rare exceptions. If, in the next decade, it turns out that vast numbers of these massive, mature galaxies truly filled the early universe, then scientists may need not just to tweak a few numbers or processes, but to write new chapters in the story of cosmic evolution. This would have implications for everything, from the nature of dark matter to the mechanisms of star formation, and even the history of elements themselves. On the other hand, if careful, repeated searches keep the numbers very low. Models may need only modest updates to explain a handful of outliers. Either result is scientifically significant. The process of long, careful search, measurement, double-checking, and open collaboration is how science sorts out fact from fluke, and how even the strangest single observation, when repeated and confirmed, changes our understanding of the universe. Above all, the push to find more ancient, mature galaxies is about matching theory with reality. Whether these galaxies turn out to be rare anomalies or plentiful building blocks in the young universe, their discovery is a milestone not just for astronomy, but for everyone interested in how our universe really began and how quickly it managed to organize itself into the vast, diverse landscape we see across the night sky today. As the worldwide search for early, mature galaxies ramps up, and the James Webb Space Telescope continues to fill its archive with astonishing data, the potential scientific impact of these findings is coming into sharper focus. The excitement isn't just about ticking off more ancient galaxies on a cosmic list, it's about what these discoveries could mean for science as a whole. If it turns out that the early universe was packed with massive and organized galaxies far earlier than most models allowed, the entire landscape of astronomy and physics could shift. The ripple effects would not be limited to people who study stars and galaxies. They would touch other fields, inspire new research, challenge textbook knowledge, and push technology on multiple fronts. At the most direct level, if multiple impossible galaxies get confirmed, and their properties can't be squeezed into existing models, cosmologists and physicists will have to go back to basics. Whenever a prediction fails so dramatically, it's a prompt to re-examine foundational ideas. This means reviewing the way dark matter clumps, the processes that cool gas and form stars, and maybe even the behavior of cosmic expansion and the laws of gravity. Scientists may have to develop new explanations for how the universe built complex structure so soon after the Big Bang, and this could involve introducing new physics or fine-tuning elements of general relativity, particle physics, or cosmic feedback effects that until now seemed well understood. For galaxy evolution, this would be a revolution. Years of computer simulations and theoretical models are built around the idea that galaxies grow slowly by merging, cooling, and assembling structure in a gradual hierarchy. If evidence continues to grow that this process happened orders of magnitude faster in the first 500 million years, it means the current foundation is missing something crucial. researchers might redefine what normal galaxy growth looks like, including a much wider variety of growth tracks in early cosmic times. Massive, well-organized galaxies in the universe's infancy wouldn't be freak occurrences, but potentially a major population, ranking alongside the smaller star-forming clumps thought to dominate the first light. This shift would mean much more than technical corrections. Graduate students, postdoctoral researchers, and professors would all be prompted to dream up new research projects aimed at testing and refining the new ideas, creating a burst of scientific creativity. The next generation of doctoral dissertations could focus on alternative models of dark matter, simulations with wildly different feedback scenarios, or hunts for new signals in the cosmic microwave background that could reveal hidden clues about early structure formation. Large research collaborations, previously geared to test old models, would shift to designing new tests and targeted observations that push the boundaries of what's possible, building on the James Webb's legacy. Related fields like particle physics would also get a boost. If standard cosmology needs revision, it could point toward the existence of unknown particles or forces. For example, the nature of dark matter is still mysterious, but if galaxies consistently mature earlier than expected, it might signal the need to imagine warm dark matter, self-interacting dark matter, or even something entirely new. This gives experimental teams worldwide fresh angles for design, from underground detectors to advanced particle accelerators, all trying to hunt for traces of the fundamental stuff that shaped the universe's earliest moments. The results wouldn't just tweak cosmic history. They could reset the search for what the universe is made of at the deepest level. Astrophysics as a broad discipline would gain a deeper appreciation of cosmic diversity. Right now, there's a sense that the history of the universe follows one main track, a hot, dense origin, cooling into simplicity, then slowly building complexity over billions of years. If instead, the cosmic dawn was crowded and fast-moving, with many evolutionary routes, it could change the way researchers frame every problem, from how to interpret the light of distant galaxies, to what kinds of stars are possible, to how and when supermassive black holes appeared. This kind of flexibility could also create new frameworks for explaining the variety of galaxies seen today, which range from giant ellipticals to small, irregular dwarfs. Another area where change would echo out is the study of cosmic chemical evolution. For mature, metal-rich galaxies to exist at high redshift, the intergalactic medium must have been enriched much sooner and faster, indicating multiple generations of stars lived and died well before models predicted. The chain reaction of star birth and death, and the pace of enrichment, would need recalculating. This could change the understanding of when and how habitable environments for planets became possible, and when the first heavy elements needed for planets, and, much later, life, were forged. Astronomy education would also face an update. If the discoveries made with the James Webb Space Telescope reshape the story of cosmic evolution, new textbooks will have to describe a universe where the action and complexity start sooner. Public lectures, documentaries, and curriculum for students at every level would begin introducing the new timeline, showing how discoveries with powerful telescopes can upend even the most basic assumptions. This offers new entry points for teaching about the Big Bang, the importance of observing different wavelengths, and the methods scientists use to compare theory with evidence. Technology and engineering will also follow in the footsteps of this research. As astronomers probe fainter, more distant galaxies, and look for even subtler signals from the early universe, their requirements push for better detectors, bigger mirrors, colder satellites, and smarter data analysis. The pursuit of cosmic origins has already produced many advances in optics, image processing, cryogenics, and spacecraft stability. Confirming and exploring a fast-paced, complex early universe will drive further investment in infrastructure, for example, the design of the next generation of space telescopes, more sensitive spectroscopy instruments, and more efficient supercomputers to crunch the ongoing flood of data. Collaboration between countries and across fields could be expected to grow substantially. International teams have already coordinated to plan and use the James Webb Space Telescope. But if its findings trigger a major revision of cosmic history, even more resources and coordination would be channeled into multi-decade projects. As new questions arise about fundamental physics, the lines between astronomy, physics, data science, and engineering would continue to blur. Funding agencies, private institutes, and university consortia could target big key projects aimed at testing whatever new early universe recipe comes out of this process. As hints about an energetic, crowded cosmic dawn keep emerging, humanities disciplines such as philosophy, science, history, and even the arts could draw new inspiration. Shifting the cosmic timescale, or the expectations for early structure creation, always prompts people to rethink human curiosity itself and the journey of discovery. New themes might pop up in museums, public exhibitions, and creative works, using the James Webb as a symbol of how deeply people can rethink the universe. One practical aspect of these discoveries is the way they change the questions astronomers ask. Instead of simply seeking when the first galaxy formed, researchers now want to know why some regions of the young universe were so busy, what drove the efficiency of star formation, and above all, whether familiar laws of physics held unaltered under early universe conditions. This shift from guessing about what's possible to explaining what's observed marks an important stage in scientific process. The details of these early galaxies, from their star composition to their chemical fingerprints to their black hole content, become clues for a new round of theory building. In the world outside academia, tools and software developed for this kind of research can filter down to everyday technology over time. High-performance detectors and imaging methods built for telescopes often end up in medical technology, environmental monitoring, security scanners, and data transmission hardware. Supercomputing techniques for handling massive datasets apply to everything from weather forecasting to financial modeling to social network analysis. The ripple effects of a revolution in astrophysics can end up being felt in ways few might expect when discoveries are first announced. Another longer-term effect is that discoveries like these can motivate and energize future generations of scientists. When young people see that even the most established ideas a complete timeline for the universe, or the basic recipe for building galaxies are up for revision, it brings home the importance of curiosity, creative thinking, and persistence in science. These results are reminders that science is a moving target, not a fixed list of facts. Opportunities for breakthroughs open up with every new piece of evidence, and the most exciting questions are sometimes the ones no one expected to ask. Within astronomy itself, the growing need to check, replicate, and expand on each new result will push teams to improve their techniques. There will be an even greater focus on rigorous methods for measuring galaxy ages, verifying redshifts, and confirming star populations. The push for accuracy and skepticism, triple-checking samples, cross-examining data, and constantly retesting assumptions will only get stronger, helping science stay robust as the picture of the cosmos sharpens. The competitive nature of discovery could produce small rivalries alongside collaboration. Teams that spot new impossible galaxies will race to analyze them in greater detail, make follow-up observations, and propose new explanations. This competition is healthy for pushing everyone to think critically, ask tough questions, and avoid groupthink. Beyond science, the bigger, more immediate effect might be on public interest and understanding. The story of a universe full of unexpectedly mature galaxies so soon after the beginning will naturally capture people's imaginations. There will be renewed interest in how telescopes work, what light from the past can teach us, and what's still hiding beyond the current edge of knowledge. Museums, documentaries, online courses, and outreach projects could see a surge in visitors and participants, all eager to follow the story as it develops. For planetary science and the search for life, the timeline for heavy element production is hugely important. If chemical enrichment happened faster, rocky planet sand, possibly habitable environments, could have arisen much earlier than previously considered. This opens new discussions about the age ranges and environments in which life elsewhere in the universe might develop, and may inspire rethinking strategies for the next decades of missions searching for biosignatures and habitable worlds. Social sciences might even pick up these cosmic shifts as history, psychology, and sociology study how major scientific changes affect public beliefs and cultural narratives. A re-evaluation of the history and expansion of the universe could shape how humanity thinks about its place in the cosmos and stirs interest in science-driven philosophies. The ultimate milestone is that such discoveries push researchers and society toward recognizing that science is always provisional, ready to update even on the biggest questions when new evidence demands it. Now and then, a technological leap like the James Webb Space Telescope comes along and opens a window onto phases of the universe that were once invisible. Each time this happens, textbooks get rewritten, careers are shaped, and the direction of what comes next changes course. It's worth remembering, too, how discoveries like these often point the way to the technologies, skills, and collaborations needed to tackle the next mysteries that will surface. The more researchers learn, the more precise the questions become. So when the next tool arrives, or the next force of nature is revealed, science is ready. Most of all, what's coming out of studies of the earliest, biggest galaxies is a spirit of open inquiry and patience. The willingness to challenge old models, the drive to verify claims carefully, and the creativity to build new explanations when observations reach beyond expectations. As the archive of ancient cosmic data grows, and as more scientists from more backgrounds join the effort, it's clear that a single surprising find can set the world on a new scientific adventure, touching every corner of the quest to understand where the universe came from, how it formed, and where it's headed next.